This is section 14.3, part B. Now that we understand what a conservative vector field is, we're ready for our first fundamental theorem of calculus for line integrals. This is going to be the circulation form. So notice it's going to tell us another way to evaluate a circulation integral, the integral of f dot t ds over a curve C. If f is a conservative vector field, so it has to be conservative, and it has a potential function phi, then we can evaluate this circulation integral by taking phi of b minus phi of a, where a and b are the endpoints of C. Hopefully that reminds you a lot of our FTC from Calc 1, right? F of b minus f of a. This is just a multivariable equivalent of it. All right, we're going to take a look at a couple of really important ideas that this gives us, and then we'll do some examples to practice using it. The first important idea is path independence. Now, I can't emphasize enough, the only way that we can use this theorem is if f is conservative. So everything we say here only applies to a conservative vector field. Let's assume then that we do have a conservative vector field, and we also have this curve C that joins 2 points, A and B. I'm actually going to call that C1. And then I'm going to create a second curve that also joins points A and B. Make it a little fancier this time. There's C2. Assuming again that f is conservative, the integral, the circulation integral, f dot t ds over this curve, can be evaluated by taking phi of b minus phi of a. But the circulation integral over this curve can also be evaluated by taking phi of b minus phi of a. Therefore, the circulation has to be the same no matter which path I take. That's path independence. So again, for f conservative, the circulation over path 1 is the same as the circulation over path 2, because both of them can be evaluated as phi of b minus phi of a. We say that the line integral, the circulation integral, is independent of path. It doesn't matter what path I take to go from A to B, I'll end up with the same value for the circulation. The second important idea is the idea of a circulation line integral over a closed curve. Now again, I'm assuming f is conservative. And if I have a closed curve, say right here, and actually I didn't put my arrows on these, I probably should have. We want to make sure we're going the same direction for both of them. And just for the sake of argument, let's say I start here at point A, coming around my closed curve, and because it's closed, I'm going to stop when I get back to A. So basically A and B are the same point, the beginning and the end. What does that tell me? Well, again, assuming that f is conservative, the integral over this curve C of f dot t ds is going to be phi of b minus phi of a, but since b and a are the same thing, that's just going to give me 0. So, for a conservative vector field, the circulation integral will always be 0. This is actually where I like to think of that word conservative. I had mentioned to you, I'd come back to that. If you think of this circulation integral as also representing work, you can sort of think of this as a conservation of the amount of work. You may have to put work into the system for a while to get it to go around here, but then the system will give you some work back. And so the net amount of work is actually 0. We've got a conservation going on here. And that's where I think that name makes a lot of sense. All right, so path independence and circulation over a closed curve. 2 really important ideas that we'll be able to use to our advantage to reduce the amount of calculation that we'll eventually have to do. Let's look at some examples. In example 2, we have the vector field f, which is 2x, 2y, and our goal is to verify the fundamental theorem of calculus, which I didn't prove to you, so we're going to verify here just for this specific example, by evaluating f dot dr. Notice that's just another form of the circulation integral. 2 ways, on the line segment from 1, 0 to 0, 2. So we're going to do this once using the parameterization method that we've been using. We're learning in section 14.2. And then we're going to do it again using the FTC. And hopefully we should be able to see that we get the same result. So method 1, I'm going to call it the parameterization method. It's just the old method that we already know. We are on the line from 1, 0 to 0, 2. So there's our path C. And the equation of that line, let's see, we have a slope of -2 and a y-intercept of 2. So if I want to parameterize that, I could let x be t, and y would be -2t plus 2. Be a little bit careful with this one if you parameterize this way. Notice that because of the direction, the x is the t value, and x starts at 1 and ends at 0. So I'm going to be really careful to write it that way. T goes from 1 to 0. I'll have to be careful to set up my limits of integration to reflect that. All right, I need r prime. That's going to be 1, -2. And then I need f. I've already defined the x and the y up here in r. And f is 2x, 2y. So 2x, that'll be 2t. And 2 times the y will actually give me -4t plus 4. My circulation integral, even though they wrote it that way, I'm going to do it as f dot r prime. And we are going from 1 to 0. I know it looks a little weird, but I do have to put my limits of integration in the correct order to get the direction correct on my path. So let's see, I'll get 2t, and then I'll get a -2 times -4t plus 4. And again, you can do the algebra, you can put it in the calculator just like this, whatever. I'm going to end up getting 3 when I integrate that. All right, that should look very familiar. We spent a lot of time in 14.2 using that method. Now method 2 is our new method, and we're kind of checking out this new FTC to see if it gets the same value as the old method. It better, otherwise there's something wrong with the math, and I don't think there is, so hopefully we're going to get that 3 again. First of all, to use the FTC, I can only do it if I've got a conservative vector field. So always start by verifying that your vector field is conservative. The test, remember, is f sub y equals g sub x. This is my f and my g up here in the vector field. So f with respect to y, that derivative is 0. And g with respect to x is also 0. So yeah, they're equal. It's conservative. That means that the gradient of phi, partial x, partial y, has to equal this f. And if I look at my first components, partial of phi with respect to x equals 2x. Bring the dx over and integrate. And phi is going to be x squared plus a constant that could depend on y. Same idea with the second components. Partial phi partial y is equal to 2y. I'll bring the dy over and integrate. And phi would be y squared plus a constant that could depend on x. So in this case, it looks like the c of x goes with the x squared, and the c of y goes with the y squared. So my phi is just x squared plus y squared. I now know by the FTC that I can evaluate my integral by taking phi of b minus phi of a. B, the ending point, is the 0, 2. And the beginning point is the 1, 0. So plugging that in for x and y is going to give me 0 squared plus 2 squared. Subtract 1 squared plus 0 squared. And there it is. 4 minus 1 gives me 3 again. So this does seem to be a legitimate alternative method, this FTC. I'm not necessarily going to claim that you're seeing it as a shortcut at this point, but I think when we look at some other problems, you'll start to see why it's so valuable to us. At this point, we've just kind of confirmed that it does seem to work. All right, so here are some nice situations. Let's suppose I'm not going to change the vector field at all. I'm going to stick with this vector field 2x, 2y. And I'm still wanting a circulation integral. Word left me there for a minute. But this time I'm just going to change the c. C is now the line segment from 1, 1 to 2, 4. If I'd like to find that circulation integral, I already know what the phi, the potential function, is. That's not going to change because f didn't change. So I can just say this is phi of 2, 4 minus phi of 1, 1. So if you're going to do multiple problems in the same vector field, this is a big advantage. I don't have to reset this up. I don't have to do the R, the parameterization. I'll just use the phi that I already know, x squared plus y squared. Plug in my values. And 4 and 16, 20 minus 2 is going to give me 18. All right, what about part C? Same f, I still want a circulation integral, f dot dr. This time C is the parabola, y equals x squared, between 1, 1 and 2, 4. So let's see, I've got the parabola here. And I just want this part between 1, 1 and 2, 4. Now this is a different path than I had up here. This was a straight line. This was part of a parabola. But because I have the same starting and ending points, when I set up my circulation integral by the fundamental theorem of calculus, I end up setting it up exactly the same way. Phi of the ending point minus phi of the beginning point, which means that without really doing any calculations, I know that I'm going to get 18 again. This is that path independence that we talked about. It really didn't matter how I got from the starting point to the ending point. As long as the points were the same, the value of the circulation remained the same. All right, the last one here, D, same F. So again, I know it's conservative. I know what the phi, the potential function, is. This time I want the circulation where C is the unit circle. And I didn't say, but let's assume again that we go counterclockwise. If I forget to tell you, we'll make that assumption. This is a closed path, so we would consider that the starting and ending points are the same. And so we'll say our circulation has to be 0. Phi of the end point is the same as phi of the beginning point. All right, we will come back and take a look at a few more examples of the FTC in our next video.